In a classification algorithm, the parameters that we have to evaluate a regression algorithm wouldn't work. Because in case of a regression algorithm, our dependent variable is continuous. So it can take any values. So we measure, in that case, we measure the error by the difference of the actual and the predicted values, because the values can be any number. But in this case, our predictions can only be ones or zeros, and so is our actual values also. So the only way we can go wrong is where actually it's a yes and we are predicting no, and actually it's a no and we are predicting yes. So these are the only two cases where our predictions can go wrong. So that is why the other parameters that we discussed in regression, the mean absolute percentage error, sum of squared errors, the root mean squared error, these will not apply in case of classification. So in this case, we use the confusion matrix to evaluate our model's performance. And from the confusion matrix, we can easily measure for how many cases it's a yes but we are predicting a no, and for how many cases it's a no but we are predicting a yes. So we saw the different parameters yesterday. We saw the accuracy. So let's do a quick revision also. So we used to keep the actual values on the left hand side and the predicted values on the right hand side. So let's say it is actual 1 and 0, and this is predicted 1 and 0. So we draw a table like this, and each of these boxes we give them some name. So what's the name of this? Yes, this is true positive. Okay, this is false negative. So whatever comes here is false negative, is negative for the second word. What's this one? Yes, false positive. This one is true negative. Okay, so these are the four words we have. So what are these words actually? These are counts. These are number of observations which fall into this. So remember the example which I gave you. You will have some actual values and you will have some predicted values. So we didn't talk about how these predicted values came. That we will talk about today. That is where logistic regression comes into picture. But what we assumed is, let's say using some algorithm, you got your predicted values. Okay. So you will have some of these values like this, and you will have some predicted values like this. So then you can easily count how many observations. So this is your number of rows. This is your number of rows, and this is your dependent variable, and this is your predicted value. So you have some independent variables also here. I have not shown that here. I'm just shown the actual values and the predicted values. So then we saw the parameters that we use to evaluate the model. We have one parameter called accuracy. So accuracy, it just measures these two. So the true positive, how many were actually a 1 and you predicted a 1. Okay. Similarly, how many were actually a 0 and you predicted a 0. This divided by total because you want it as a percentage. Okay. So into 100 percentage. Similarly, you have the error parameter, which is opposite of this because we know that these two are error parameters. These two is where we went wrong because actually it was a 1 but we predicted a 0. Similarly, in this case, actually it was a 0 but we predicted a 1. So this will be false positive plus false negative divided by total. Okay, and of course accuracy plus error should be equal to 1 because we should get a total of 100%. Then later we saw why accuracy should not always be used to evaluate models performance, because we saw one example that, let's say you have 100 total observations and out of that 99 are zeros, and there is only, or let's say 95 are zeros and 5 of them are ones. So in this case, even if you predict that all 100 are zeros, you will still have an accuracy of 95%, but this model will be useless because it is not able to identify anyone. So that is why, depending on the scenario, we either use the accuracy or we don't use the accuracy. So in cases where identifying ones is important, Or you can say identifying ones is more important than identifying zeros. There we use sensitivity or recall or true positive rate. Okay, anybody remembers the formula for this? What is the formula for sensitivity? Yes, since it is called true positive rate, so it will have true positive as the numerator. And remember, it will have the row total as denominator. So the row total is this, the actual ones. So this is the actual ones in your data. So I'll write true positive plus false negative. Okay. So this is your sensitivity. This measures, this gives importance only to identifying actual ones. Okay. So see, accuracy has both true positive and true negative. But here I have given just true positive. So it measures only out of all actual ones, the denominator is all the actual ones, this number. Okay, so out of all actual ones, how many ones it has identified? So these are the ones it has identified correctly, right? Whatever is in this box. So out of all actual ones, how many ones has it identified? That is what sensitivity, recall, or true positive rate measures. Similarly, you have specificity also. So this measures opposite of this. It measures zeros. Okay, it measures zeros only. So you will have true negative divided by the row total. So false positive plus true negative. So this is the true negative rate. That is specificity. It measures out of all actual zeros, how many zeros are you identifying? This is what it measures. So that is specificity. And then finally we have one more parameter, which is precision. So what's the use of precision? Why do we use precision? Yes, anybody? First, tell me the formula for precision. First, tell me the formula for precision. What is the formula for precision? Yes, true positive divided by the column total this time. So for both these two formulas, we have used row total. This time it will be column total. So the column in which true positive is present. So it will be this column. So true positive plus false positive. Okay. So what does it measure? Anybody from yesterday's class? Do you remember what does it measure? Why do we need precision? Did you revise the videos once? Yeah, sometimes we can't go with the true positive rate, hence precision. So why sometimes we can't, in which cases we cannot go with true positive rates, anything more you want to say? Why can't we go with the true positive rate always? And how will precision help in that case? Yes. So if we always go with the true positive rate, then we will get 100% true positive rate in cases where all predictions are ones. Okay. So let's say you have a model which always predicts one, which never predicts zero. So in that case, if you measure the sensitivity or the true positive rate, you will get 100%. So you will misunderstand that it's a very good model because it has a sensitivity of 100%. But actually that model is predicting one for everybody. So that is why we have to put a check on that. We have to put a constraint so that none of the models predicts like this, or the model never predicts like this. So that is what precision does. Okay. This is what precision does. It puts a check on sensitivity and prevents the model from always predicting once. Okay, so that is why, what is the interpretation of precision? It measures out of all predicted ones, how many were actual ones. Since the denominator is all predicted ones, if you predict too many ones, this number will become small, and you will know that your precision is not good, since the denominator is all predicted ones. So if you predict 100 ones out of 100 samples and only 5 are actually ones, your precision will be only 5%, which is very poor. So you will know that your model is not doing good. It is over predicting. It is always predicting one. Or out of all 100 predictions of one, only 5 are actually ones. So this is like shooting in the dark. Okay, so you have shot 1,000 times in the dark and 100 times in the dark, and 5 of them hit the target. So will this be good? No, this is not a good. 5 times you have hit the target, but look at the number of times you have tried. You have tried 100 times and then 5 times you have hit the target. This is just like luck. Obviously, so many times if you shoot in the dark, a few of them might hit the target. Okay, so that is why precision is used, to put a constraint on sensitivity so that the models don't over predict once, because predicting once is not easy, it is costly. Okay, later you will see in some business scenarios. So for example, the cancer thing, you cannot always predict for every patient that he or she has cancer. That will be like looting the patients. Okay, all clear so far, guys? So now let us see how do we get the predictions. In case we have seen, after getting the predictions, how do we evaluate our model? Now let us see how do we get the predictions. So now let us start with logistic regression algorithm. Okay, so it's called logistic regression. So first let us look at the name. So look at the word regression here. Why do we have the word regression? We have the word regression because the idea here, the idea in logistic regression is stolen from linear regression. Idea is stolen from linear regression, and that is why it is called logistic regression. So what do we have in linear regression? We have y is equal to beta naught plus beta 1 x1 plus beta n xn. This is what we have in linear regression. Now what can be the values of y here, guys? Can you tell me what can we have as values of y's here? What can be the range of values of y? What can be the range of values of y? Yes, continuous, but what values? What is the range? If I have to write a upper limit and lower limit, what should I write for y? What can be the upper limit of y? What can be the lower limit of y? For any values of x. So these are the variables we have. Let's say for any value of x, what can be the upper limit of y and lower limit of y? Yes, exactly. It can be anything. So it's a line. So it can go till infinity, it can go till minus infinity. So the y-axis can be infinity and it can be minus infinity. Just put infinity as x and y will become infinity. or just put minus infinity and as one of the x, it will become minus infinity. So the range it can take is minus infinity to plus infinity. It can take any values between this range. Now, how can we use this in logistic regression? Because we know in logistic regression, our values can only be ones or zeros, right? It can only be ones or zeros. It cannot be anything else. So how can we utilize this equation and meet this constraint also? So our constraint here is that our output should always be between ones and zeros. Okay, if it is between ones and zeros also, that is okay, because we can put a threshold and we can convert. So it need not be just 1 or 0. Let's say our value is 0.8 or our value is 0.3. Then what we can do, we can say that, let's say we have a threshold as 0.5. So we have 0.5 as threshold. So we can say whatever is above 0.5 is a 1 and whatever is below 0.5 is a 0. Okay, so we can do that. So if we get a number between 0 and 1, or if we get a probability, I should say, if we get a probability, I can easily convert it to ones and zeros by applying a threshold. This 0.5 is called threshold. Threshold means, so you have probabilities from 0 to 1, and you put a threshold somewhere in the middle and you say whatever is below this is 0, whatever is above this is 1. So that we can do. Okay, that is not a problem, but we should not get something which is outside of 0 and 1. That would not make sense. If we get something which is outside 0 or 1, that will not make sense. So but how can we do that? How can we convert the output y here between ones and zeros? So that is where we use a function called logistic response function. Okay, so to do that, what we will do is we will take this y, and we will apply some function g on top of it. Okay, we will apply a mathematical function g on top of y, so that the output is always between 0 and 1. Okay, we will apply a function on top of this so that the output is always between 0 and 1, and that function g is called logistic response function. So it's a mathematical function which we apply on top of y. Why do we apply? So that the output is always between 0 and 1. Why do we need our output always between 0 and 1? Because we are dealing with a classification case. So a value of 5 or minus 10 will not make sense here. It may make sense in linear regression, but in logistic regression it will not make sense. What is 5? Is it 1 or is it 0? We don't know. What is minus 10? Is it 1 or is it 0? We cannot say. So we need the output to be between 0 and 1 as a probability. We need the output as a probability. Only then we will be able to convert it to zeros and ones. Okay, so we achieve that by applying the function logistic response function. Now let us see what that function is. So this is that function. I'll directly write the shape of the function. So this is that function, logistic response functions. Okay, so this function is known as logistic response function. If you see, you have the same linear regression line here. This is the linear regression line. So what I have done is this g function I have written here. Okay, it is the same linear regression line, but after applying the function g on top of it. And the left hand side is probability of y is equal to 1. So what this gives you is, it gives you the probability of y is equal to 1. So you get a probability between 0 and 1, and let's say if your probability is above 0.5, this is 0.5. If your probability is above 0.5, so probability of 1 is above 0.5, that means you can convert it to 1. And similarly, if probability of 1 is below 0.5, you convert it to 0. Okay, this is the logistic response function. If you see, it will always have a value between 0 and 1. How will you prove that? You just put some values. So what is the maximum positive value we can have for x1? The maximum positive value we can have is infinity. So let's put infinity here and see what value of probability we get. So I'll put infinity here. So what will I get? Infinity into some constant. So this entire number will become infinity, but I have a minus sign. So it will become minus infinity. So I will get 1 divided by 1 plus e to the power minus infinity. Okay, this is what I will get. So this I can write as 1 plus e to the power infinity. Now e to the power infinity will be infinity. So I'll have infinity as the denominator here. So I'll have 1 divided by 1 divided by infinity. Okay, this is what I will have. Now 1 divided by infinity will be, what will I get? Yes, guys. 1 divided by infinity is infinity. So e to the power minus infinity is 1 by e to the power infinity. Okay, or let me do it this way. So I'll get this, then I can write e to the power infinity plus 1 divided by e to the power infinity, right? I can write this. Okay, now what will I get here? E to the power infinity is infinity, and here I will get 1 plus infinity, right? So I will get basically infinity divided by infinity. What is that? Which is equal to 1. Okay, so that means if you put infinity here, what you get is 1. Okay, and let's put minus infinity here. I'll put minus infinity now. So this number will become minus infinity. So what I will get is minus minus will become plus infinity. So I will get this. So 1 divided by infinity I will get. 1 divided by infinity, what is that? It will be 0. Right? So divide 1 by a very big number, you will get something around 0. So that means no matter what you give, your output or your probability of 1 will always be between 0 and 1. So we just gave infinity and we checked. You cannot give any other number, right? Whatever numbers you will give will be between minus infinity and plus infinity. So definitely it will be between 0 and 1. Okay, so this is what the logistic response function does. It reduces the output between zeros and ones. Any doubts on this? Think on this for 10-15 seconds and tell me if you have any doubts. Okay, so Anupama is asking why is it probability of y is equal to 1? Why not probability of y is equal to 0? Because it is often seen that y 1 is your variable of interest. So for example, if you are a cancer hospital, will you look for actual cancer patients, or will you look for patients who do not have cancer? What will you look for? So it both of them mean the same, because if you can find one, you can automatically find the other. Okay, but if you are a cancer hospital, your goal will be to identify cancer patients, right? That will be your goal. Your goal will not be to identify the non-cancer patients. That is why we always look at one. Okay, we always look at one. One is often the variable of your interest, not zero. So people who default their loans, or people who will not pay back their loans, those are the people in of interest, not people who will pay their loans. People who do not pay their loans, that is the variable of your interest, so that you can avoid giving loans to those people. Okay, is it clear now, Anupama? Okay, so this is about logistic response function. If I draw a plot of this function, if I draw a plot, it looks like this. So if I have probability of y is equal to 1 on my y-axis, and if I have beta naught plus beta 1 x1 plus beta n xn on my x-axis, the plot will look like this. It looks like this. Okay, where this point is 0.5 and this is your 1. This is obviously your 0. So you see it always lies between 0 and 1. It almost never touches 0, and similarly it almost never touches 1. Okay, so it is always between 0 and 1. It never goes outside it, of course. But remember what is the y-axis and what is the x-axis. Okay, the x-axis is the linear regression line. The y-axis is probability of y is equal to 1, not probability of y is equal to 0. Okay, this is also known as the S curve because it looks like a S. Okay, any doubts so far, guys? Okay, now there is another concept. Let us talk about that. Now, logistic regression is also often seen in terms of another parameter called odds. There's another parameter called odds that is used. So what is odds? Odds has a formula: probability of y is equal to 1 divided by probability of y is equal to 0. This is the formula for odds. Now what is odds? Now this often has to do with the way English language is used. Okay, so this is not coming from maths, but this is coming from the English language. So for example, we Indians, see we often, while talking in English, we often say what is your probability of doing something, right? We always talk in terms of probability, but native English speakers, they often talk in terms of odds. They don't use the word probability because probability is like a technical word. It comes from maths. So what they use instead, they talk in terms of odds. So what is your odds of doing this? So if you watch a lot of English series or movies, you would have noticed this, or maybe next time you watch you will notice that they talk in terms of odds. What are the odds of this happening? So it's similar to what probability can be used for. What are the probability of this happening? But they talk in terms of odds because this is more commonly used. Okay, so what is odds of this comes from actually from horse racing. In horse racing they use this a lot. What are the odds of this horse winning the race? Okay, so it has this formula. Okay, it has probability of y is equal to 1 as numerator and probability of y is equal to 0 as the denominator. So we can now plug the logistic response function's value here, and we can break this down. So I can write this as 1 minus probability of y is equal to 1, and then here I can plug that logistic response function. So if I plug the logistic response function here and here, so remember the logistic response function is this. where theta is equal to the linear regression line. Okay, I have written theta in place of this so that I avoid writing it again and again. So if I plug that here, let me plug it. 1 divided by 1 plus e to the power minus theta, and here 1 minus 1 divided by 1 plus e to the power minus theta. Okay, this is what I will have. Now if I solve this, if I break this apart and if I do all the subtraction and all, what I will get at the end, let me write that directly. I will get e to the power theta at the end. You can do this yourself and you will see this is what you will get. You will get odds is equal to e to the power theta. Okay, now taking log on both sides. After this I will take log on both sides. Then I will get log of odds. Okay, log to the base e I will take. Log of odds is equal to theta. This is what I will get, right? E log e is 1. So I can write this log of odds is equal to beta naught plus beta 1 x 1 plus beta n xn. So this is also the equation of logistic regression in terms of odds. Okay. Log of odds is also known as, this is also known as logit. Log of odds is also known as logit. Okay. So this is another form of writing the equation of logistic regression, where you write log of odds or logit is equal to the linear regression line. Okay. This is another form of writing the logistic response function or logistic regression equation. But we will mostly be using this one because we want probability as output. We don't want log of odds. We want probability of y is equal to 1. We don't want log of odds, but you should know this. Okay. Any doubts on this? Logistic regression is not difficult. It is quite simple. Guys, any doubts so far? So what process will we follow? We will follow. So running this in Python is very simple. You just have to call a few lines of code, just like you did in linear regression. You will be calling a few lines of code and you will get your predicted values. So whatever example I showed you, you will have your actual values in your data and you will get your predicted values. Now you might get your predicted values as a probability. Okay, it depends on your wish. If you want as probability, you can get it as probability also. Okay, so you can get as probability and you can convert, because our actuals will always be ones or zeros. So you cannot compare these two. You cannot compare 1 with 0.1. Okay, because remember the confusion matrix will only take ones and zeros. It will not take zero point 0.1 or something else. It has your predicted values has to be 1 and 0. Only then you can form the confusion matrix and create all the parameters. Okay, so you will have to convert your predicted values to ones and zeros. Now how do we do that? So now we know that our predicted value will always be between 0 and 1. Why it will be between 0 and 1? Because we are using the logistic response function. We are using the logistic response function, and we know that it always lies between 0 and 1. It cannot go outside of it. That is why I'm saying your predicted probability, which is nothing but the probability of y is equal to 1. This will always be between 0 and 1. So now what you can do, you can use a threshold. You can use a threshold, let's call it t, and using that threshold t, you can convert it to, so whatever is below threshold, you will say it's 0. Whatever is above threshold, you will say it's 1. This way you can convert your predicted probabilities to ones and zeros, and once converted, you can easily create the confusion matrix using this and this. Okay, so this is the approach that we will follow. Okay, we will talk about the threshold value in details. What threshold to take? Should we always take zero point 0.5 because it is right in the middle, or is there another way to calculate the threshold, or is there a better way to look at this threshold's value? We will see that. Okay, but so far, is everything clear, guys? Have you followed the approach? It is not very difficult. It is easy, fairly simple. No, S curve will not give you the threshold value, Amit. S curve is the logistic response function. It will give you the probability. Threshold separately you will have to decide. I am yet to talk about that. I haven't told anything how to decide the threshold yet. The S curve will just give you the value of probability. So look at this. Look at the S curve. What is the y-axis? What is the y-axis for S curve? The y-axis is probability of y is equal to 1. So it will only give you probability of y is equal to 1. There is no threshold here. Okay, it will give you probability of y is equal to 1, and then you will use a separate concept to decide the threshold. I'm yet to talk about it. So now we'll quickly see how to run logistic regression in Python. It is very easy. It is exactly how you run linear regression. Just you will change the function. Instead of writing linear regression, you will write logistic regression. That's the only change. All other things remains the same. And there will be a slight change in evaluating the model. So previously you were calculating MAPE, RMSE, SSE. Now you will calculate accuracy, sensitivity, specificity, and so on. Okay, that's the only difference. But the codes pretty much remain the same. So this is a case study. I'll not go into the details of the case study. I will share this with you later. But so during this week I will share this with you. But what I want to focus on here is how we run logistic regression. It is very simple. So let's say this is the data. This is the data, okay? So the variables are described here, all the variables. This is the data. And after doing some EDA, this is where the model building starts. So you see what have I written here? I have written from sklearn dot linear underscore model import logistic regression. If you remember what you did in linear regression, instead of logistic, you wrote linear regression there. All other things remain the same. Okay, just this has changed from linear regression to logistic regression. Okay, and then look at this. This is the same what you did earlier. You have divided your data into training and test. Okay, so this is the same variable, and here you have decided which variables do you want to use as independent variables. Now I have a lot of independent variables. If you see here, I have a lot of variables, but I'm not using all of them as independent variable. I'm only using 4 of them. I'm only using these 4 of them as my independent variable. Okay, and of course before you use independent variable, you will have to convert the categorical variables to dummy variables. So remember, we used to convert the categorical variable to dummy variable. So if you have any categorical variable, you will have to convert that to dummy variables using the same concept that we did earlier. Okay, so don't forget what you have learned in linear. And then you will split the data into train and test, and then you will run as you had earlier. So logistic regression, you will fit the model by giving the independent variable of training data and the dependent variable of training data, and then you will predict. So how will you predict? You will write the name of the model dot predict, same way as you did for linear regression. Okay, yeah, all that is done here, Arpita. I'll come to that. Okay, correlation check is not required here. You cannot do a correlation check with the dependent variable because the dependent variable is only 1 and 0. So there is no meaning of correlation here with the dependent variable like you used to do in linear regression. In linear regression, you used to check the correlation of dependent with the independent, right? That cannot be done here because the dependent is only 1 and 0. So you cannot find correlation with a variable which is only 1 and 0. Correlation means both the variables has to be continuous. Okay. Yes, multicollinearity we will have to check. Okay, I'll come to the assumptions of logistic regression later. So park that discussion for a time being. Okay, so this is what I have done here. Then I have predicted, and after predicting, what have I done? If you remember the cross tab function, guys, we had seen this in the initial days when we were learning Python. The cross tab function we will use to compute the confusion matrix. So this is the confusion matrix. This is your confusion matrix. Okay, so this is your actual zeros and ones. So since I have written y train here, that is why I am getting actual 0 and 1 on the left hand side. If I write it in an opposite way, I will get it opposite way. So always remember, guys, your confusion matrix will not always look like this. It might look, your predicted values might come here and actual might go there, because if you give that as your Python code. So pandas dot crosstab is what we use. Okay, so whatever. No, you don't need to know that, Anupama. You don't need to know that. Okay, so pandas dot crosstab, this is the function that is used to create the confusion matrix. So whatever you write first, that will become your left hand side. Whatever you write second will become your right hand side. So always give your actual values on the left hand side so that you get it in this format. If you give your predicted values on left hand side, your predicted values will come there. You can still compute the confusion matrix using the cheat code which I gave you, but it will become a little tricky. So we always follow this norm. So you give your actual values. What is your actual value? Your actual value is y underscore train. And what is your predicted value? This is coming from the model. So pred. Okay, this way you can compute your confusion matrix. So this is what I have. So this is 0 0, that means this is true negative. This is 9 1 1, that means it is true positive. Okay, so this is on the training data. So if you see, I have predicted on the training data only. I have passed the x or the independent variable of training data. Similarly, I can predict for test data also. So I predicted for test data, and this is the confusion matrix for test data. So I can find all the values now. See, this is true positive is 7. Similarly, all the other parameters I have written, and then I have computed the accuracy. Then I have computed the error, and I have just printed. So accuracy is 75%, error is 25%, and these are the coefficients. Coefficients means betas, because here also we have betas, right? In logistic regression also we will have betas, right? We have the same equation basically, so we have betas here also. So those betas are what I have printed here. So these are the 4 betas. I have 5 variables, not 4. So days since last year visit, narcotics, pain, total visits, and true. So I'll have 1, 2, 3, 4, and 5 coefficients I will have, plus 1 intercept. Okay, so that is what is given here. 1, 2, 3, 4, 5 coefficients and 1 intercept. Okay, so this is how, and this is finally the equation. This is the equation that you will get finally. This is the logistic response function. Okay, now if you want to get probability out, so remember I told you that you can get probability out if you want. So here I have not gotten probability. If you see, I have directly gotten ones and zeros because I have used the function predict. If you want the probability out, you can use another function called predict underscore prob a. Okay, if you use predict underscore prob a, you will get probability as the output. Okay, is that clear, guys? We will talk about why do we get the probability out. If we can directly get ones and zeros, why do we need to get the probability out? So why are we getting a directly ones and zeros here? Because Python is using a default threshold of 0.5. Okay, that is why we are getting directly ones and zeros, because Python is using a default threshold of 0.5. Okay, a default threshold of 0.5. But sometimes we will see that using a default threshold of 0.5 is not the best approach. That is where we will use the function prob underscore a, and we will apply some other threshold, maybe 0.3 or maybe 0.7. We will change the value of threshold from the default value of 0.5 to something else. That is where we will need the probability. Okay, are you following, guys? Sure, Sinu. So what I will do is, let me write down the steps here. It is the same. So it is not different. You can just copy paste. So just like you used to do in linear regression, first you will import logistic regression function. Okay. So linear from sklearn dot linear model import logistic regression. You will import this function, then you will create an empty object. So let's say I'm creating an empty object logreg. Logreg is equal to logistic regression. You will create an empty wrapper just like you did in linear regression. Then in this empty wrapper you will pass the, so logreg dot fit, you will pass the training data. So training data is x underscore train and y underscore train. So your model fit is done. Once your model fit is done, let's say I'll put it as LM. Okay, Once your fit is done, you can use the predict function. So you can use lm dot predict, and then you can pass your x variable of test. If you want to predict on the test data, you will get ones and zeros. Okay, you will get ones and zeros for all rows in the training data. So you see, you are only passing the independent variable, and what you are getting is, let's say, predictions. This is your predictions. You can compare this with the actual values, in test data, which is y underscore test. Y underscore test is the actual value in test data, and you can compute a confusion matrix. So y test 0 and 1, and this is your pred 0 and 1, and you can create the confusion matrix. Okay, or so here we will directly get ones and zeros because it is using a default threshold of 0.5. So 0.5 is being used as the default threshold. If you don't want to use 0.5, you use the function dot pred underscore prob a, and you pass the same independent variable of test. So here you will get probability. You will get, let's say, anything. You can get any number. Okay, now using directly these numbers, you cannot prepare the confusion matrix. So what you will have to do, using if else in Python, you will have to convert these numbers to ones and zeros. So you will take a threshold, let's say t, and you will say whatever is above t, it is 1, whatever is below t, it is 0, and then you will convert these numbers to ones and zeros. And once these are converted to ones and zeros, you will compare it once again with the actual test, y test 0 and 1, and these numbers whatever you have gotten 0 and 1, and you will once again prepare the confusion matrix and compute all the parameters. Do you follow now, Sinu? Don't worry, in the assignment I will try to give you a structured approach. So once I put something in logistic regression, I'll give you a structured approach where you will be able to follow. Okay, so I'll give you maybe 5 or 6 questions where one by one you will be following and doing these steps. Then it will definitely become clear, and also watch the recordings multiple times. Yeah, that's what we will talk about. That's what I'm saying, Amit. Every time I'm repeating the same thing to you. I'm yet to talk about the threshold. I will talk about it first. Understand this concept, then I will talk about the threshold, because that is a little tough topic. So I want to talk about that after the break, not now. So after the break, once you have rejuvenated, then I will talk about that. So it involves something called a ROC curve that you see here. Okay, so I'll talk about that after the break. Okay, so any doubts so far, guys? So I've started pasting the notes also below the link. So these are the notes. You can see the notes if you want. And Anupama, I think you were asking about the codes, right? The codes will always be here. So whatever class codes I am referring, you can go to any of the module. Let's say I go to linear regression. This is the day 5 classes that we have. You will have the notes that are used, or the codes here as resources. Okay, it's here. We do not have anything. So these are the codes. You can just click here and it will ask you to download. You can click there and you can download the codes. Okay. So this quiz, I'm still working on it. Don't start on this, guys. I'm still working on this. By today this will be ready. And by tomorrow I will get this ready. The case study for linear regression, I will have that ready also by tomorrow. And in the next 2 or 3 days I will have one quiz for logistic regression. Not just one, I will have several small quizzes and one big quiz, one big case study for logistic regression. And I will have one application separately like this for logistic regression also here. One separate module just for logistic regression to practice the hands-on part. Okay. So let's do a quick revision of what we have seen so far. Quickly, let's revise. It's the same. Those processes will remain same, Naresh. That has nothing to do with the algorithm. How do you replace missing values? All those processes will remain same. That has nothing to do with individual algorithms. So whatever suits best to the business, whatever suits best to the current data, accordingly you will decide, and that is something which is subjective. Okay, so you take your call and decide what should be the best value of something which is missing. Okay, just like we had done earlier, on a case to case basis you will decide what should be the best value to replace the missing values, or if you have outliers in your data, how should you replace the outliers. Then you take the mode. If feature has only ones and zeros, and let's say there are 80 ones in your data and 20 zeros, then the missing values you replace it with ones because there are more ones in your data, for example. Okay, so this will remain the same as before, no changes here. In fact, in all the other algorithms also this will not change. This has nothing to do with the algorithm. Okay, so what did we see in logistic regression? We saw that logistic regression is just an extension of linear regression. Okay, we take the linear regression line, and we apply a function on top of it. This function is called the logistic response function. Okay, so this function gives you the probability of y is equal to 1 as a function of this, where theta is your linear regression line. Okay, this looks like a S curve. It looks something like this, where your x-axis is the linear regression line, or let me write theta directly. So this is theta, and this is your probability of y is equal to 1. So it always stays between 1 and 0, never goes outside it. This is what we saw. Then next, we saw the concept of odds. This is another way to evaluate or understand logistic regression. The formula for odds is y is equal to 1 by y is equal to 0. If you do everything, if you put this equation here and here, what you will get is e to the power theta. So if I take the log of odds, which is also known as logit, I will get theta. Okay, so this brings us to the first assumption of logistic regression. So let us talk about assumptions of logistic regression right here. Okay, there are not many, only two assumptions of logistic regression. Okay, so the first assumption is that log of odds should have a linear relationship with x. So what are we getting here? In this equation, we are getting log of odds or logit is equal to beta naught plus beta 1 x1 plus all the others. So what can we say here looking at this? That means this should have a linear relationship with your variable x, right? Similarly, in linear regression, we used to say, right? In linear regression, if you remember, we used to say y should have a linear relationship with x, right? So similarly, in place of y, we have log odds here. So here we can say log of odds should have a linear relationship with x. That's what I have written here. Log of odds should have a linear relationship with your x. Okay, this is the first assumption of logistic regression. And second assumption is there should not be any multicollinearity. This is same as linear. There should not be any multicollinearity in data. That means even here you will have to check that the correlation between x1 and x2 is not high. The correlation between x1 and x2 should not be high even in logistic regression. Okay, it should be low. It should be low for logistic regression also. Okay, do you follow? Do you follow the two assumptions, guys? Okay, so we have these two assumptions in logistic regression. First is that log of odds should have a linear relationship with the independent variables. And second is there should not be any multicollinearity between the independent variables. Okay. Okay. Now in logistic regression also you can get the output in this format because remember we have to look at the p-values. Just like in linear regression, we have the same concept of hypothesis test even in logistic regression. Okay. So here also we can get the p-values. You see, this is the p-values we are getting. So how do we get this? The same approach. Remember in linear regression, this is what we used. From stats model dot this, you import sm, and stats model add constant. You will add a constant first, and then here you will use sm dot logit function. In linear regression, you use something else. Okay, and then you pass the y values, the dependent variable, and the independent variables, which includes the constant also. Okay, and then you just run this summary function and you get the output. So you will get the p-values for all independent variables in case of logistic also. So you see all the p-values are small, are very small, almost less than 5% except this one. So this pain is above 5%, so maybe I can ignore this variable from the model. but this is how it is. Okay, this is how you can get the output in case of logistic regression also. Okay, and then you can decide which variable is important, which variable is not important by looking at the p-values. Okay, so these concepts, whatever we learned in linear regression, also applies in case of logistic regression. Okay, there is no difference there. So what remains to be talked is this deciding the threshold, which I will talk after the break. Okay, so these are the two assumptions of logistic regression. Very easy to remember. One is multicollinearity, which was same as in linear regression. The other is that log of odds should have a linear relationship with your dependent variable. Okay, so then we also saw how you can get p-values, just like in linear regression, same codes, just the name, just the function changes here from linear to logistic. We can get p-values and we can do a feature selection. Okay, remember feature selection, deciding which independent variables should be included in the model and which should not be included. So we can look at p-values, and these p-values we can get from the stats model. So the codes I'll be sharing, you can easily see the codes, not many lines of code. And don't worry, even if you don't remember the codes. As a data scientist, you are never supposed to remember the codes, but you should Google and you should understand. So you should understand what each line of code is doing. You should not, even if you don't remember, even I don't remember the codes, but I understand what each line of code is doing. This code is, for example, adding a constant. If I don't run this line, I will not get this constant in my model. This constant that I'm getting, this represents this constant that I'm adding here. Okay, and the other variables are just the coefficients for the other independent variables. Okay, this is the same standard error that we discussed. This is the z value. Remember z test, we talked about z test. This is those z values. These are the z values which are coming from z test. Okay, and based on that we have our p values, and looking at these p values we decide whether the variable is important or not. And then once again I have divided into train and test. I have built a model on train and predicted on the test, and then computed the confusion matrix, and I have gotten some accuracy. So these processes remain the same. Okay, now after the break we will see how do we decide the value of threshold. Should the threshold always be 0.5, or can we take a different value? Can we take a different value of threshold? And if we take a different value of threshold, how do we decide that different value? We will talk about that after the break. Okay, so I have almost covered everything in logistic regression except this threshold thing. So it's not very difficult. Maybe you are looking at this for the first time, so it might be a little confusing for you, but I'm sure if you revise the videos and if you give some time to this concept, you will understand. It is not very difficult. So any doubts so far, guys? Do you have any questions so far? So Anupama is asking, I didn't understand how we derive the true, positive, etc. values manually. That is not difficult, Anupama. So it's very easy. So you have your actual values, right? So in the data, you will be given your actual values, which are ones and zeros. So let me show you, for example, let's see this data. the data that we have here. So the dependent variable here is this variable. So you see it already has ones and zeros. Or if I show you directly here, so this is the data that we have. So in Excel, I can easily show it to you. So you can see this value poor care, which is the dependent variable. It has only ones and zeros. Okay, so it has only ones and zeros, and what you predict will also be ones and zeros. So let me predict. Let me just write some predicted values. Okay, so predicted values. Let me write some ones and zeros here. Oops. So let me write a bunch of ones and zeros. Oops. Okay, so let's say I have a bunch of ones and zeros here. Let me just paste it once again so that I have filled all the rows. Okay, so I have filled all the rows. So I have my actuals, I have my predicted values. Okay, now what I will do, let's say I have to find the true positive. So what is the cheat code for true positive? If you remember, what is the code we used for true positive? What is the second word? If you have to find the true positive, what was the second word? The second word was that if predicted is equal to 1, it is positive, right? Right, guys? So what I will do, I will apply a filter here. I'll apply a filter predicted is equal to 1. So I will get these numbers. Now here I will count how many are actual ones. This is my actual value. I will just count how many are actual ones. So I'll apply another filter here. So now I will get a count. So the count is 19. So that means my true positive is 19. I'll note it down. That's it. This is how we do. This is exactly how the pandas.crossTab function works. So pd.crossTab, this is the function does exactly what I showed you in Excel. And that is how you get your count of true positive, true negative, and everything. Do you follow now, Anupa? It's very simple, just applying filters and checking. Do you follow, Anupama? Any other questions, guys? Yes, similarly we did for yesterday's example also. That is exactly how we did for yesterday's example. We just applied filters on both the columns. One by one we applied filter and we counted the number of values. So always remember, the numbers that we write here are counts. These are all counts. Counts which fulfill what is there in the row and what is there in the column. So how many are actual zeros and how many are predicted zeros? That count we will write here. Similarly for these also. These are just counts. Let's talk about the ROC curve now. Okay. So first is, why do we need a different threshold? If we can take zero point 0.5 as the threshold, why do we need something else? So again, this once again has to do with what we were discussing the other day, yesterday, about the business problem. So let's say we are talking about, so this cancer example is the best to discuss in such cases. So let's say this is 0 to 1, and we are talking about probability of y is equal to 1, or probability of someone having cancer. Okay, so when we take a threshold of, let's say, zero point 0.5, okay, let's say we take a threshold of 0 0.5. So whatever is below this we classify as 0, whatever is above this we classify as 1. Now, do you think a person who has 0.49 probability of having cancer, do you think a person who has 0.49 probability of having cancer should be classified as a 0? Do you think that would be good? If a person having 49% probability of having cancer be classified as not having cancer, is that good? No, right? Of course not, because 49% is a lot, because this is life and death situation. So we should not take any chances. So in such cases, we reduce the threshold to a smaller value, let's say 20%, for example, or even less. Sometimes we even give it, let's say, 8%. So even if somebody has 8% chance of having cancer, we still say that that person is a 1, because this is life and death situation. So we don't want to take any chances. Point 1 maybe not. Point 1 maybe not, because point 1 is too small. 0.1% if you are talking about. Okay, if you're talking about 0.1%, then maybe, because nowadays, with so much adulteration in food and everything, I think probably everybody will end up having 0.1% of 0.1% chance of having cancer. 0.1% is very small, right? So that means 1 in 1,000. That's very small. Okay. But yeah, again, it depends. This is my understanding. This is what I'm saying from my perspective. It might differ. This is something subjective. But yeah, depending on the disease, we can decrease the threshold. If the disease is very uncommon, then probably zero point 0.1 would make sense. But I don't think cancer is an uncommon disease now. It is quite common. Okay. So depending on the disease and how common or uncommon the disease is, we can vary the threshold so as to reduce the risks involved. So if somebody has even 10% chance of having cancer, we would still classify that person as having cancer. Okay, just to reduce the risks. Okay, so that is why we would need this threshold value. Now you may ask, why, when do we can also have a threshold of, let's say, 80%. Okay, we can also have a threshold of 80% at times. Now, why would we have a threshold of 80%? Let's say a company is very low on budget, or let's say you are a company, you are the CEO of a company. Okay, you are the CEO of a company and you have built an employee churn model. So employee churn model is a model which predicts which employee is planning to quit. Okay, which employee is planning to quit, which has not quitted yet, who have not quitted yet but are planning to quit. And let's say you have some 1 lakh employees. You have 1 lakh employees, and out of that, let's say you got ones for 10,000, and for 90,000 else you got zeros. Okay, this is what your model is predicting. For some 1,000 of, for some 10,000 of them, your model is predicting 1, and for some 90,000 of them, your model is predicting 0. Okay, and you don't know the actual value because these employees are yet to quit, so you don't know the actual value. This is your test data. Okay, you don't know the actual values for these. You have predicted this. But let's say, and the CEO decides that I will pay 1 lakh as bonus to all the employees who are planning to quit so that they don't quit. Okay, the CEO decides that I will offer as bonus of 1 lakh rupees to all the employees that this model predicts are planning to quit so that we can retain them. Now, but the CEO also tells that I only have a budget of, let's say, 1 crore. the CEO also tells that I only have a budget of 1 crore. I cannot give more than 1 crore. That means only 200 employees I can pay. I cannot pay more than 100 employees. But here, if you see, I have 10,000 employees as one. So which 100 would you pay? Which 100 of them would you pay this 1 lakh each? So that means here we have taken, let's say, threshold of 0.5. So what we will have to do, we will have to increase our threshold in this case so that we get fewer employees. So that only if we are 80% sure, so a threshold of 0.8 here would mean that only if the model is predicting with 80% probability that an employee will quit, only then we are classifying as one, not otherwise. If the model has 50% chance if the model says with 50% probability that an employee is planning to quit, we will not give him 1 lakh rupees, because every employee has 50% chance of quitting for better opportunities. We will give 1 lakh rupees only if the chance is 80% or more of quitting. Do you follow, guys? Do you follow what I'm trying to say here? So in these cases, we will increase the threshold to a higher number. We will not give 0.5, but we will keep some higher number just so that we can meet the budget. Okay. So this is why we will have to vary the threshold at times to meet our business requirement. Doubts on this? Yes, guys. Any doubts on this? Okay, cool. Now let us see how do we do this. Okay. So we have seen the necessity of having a different threshold, but what should be that value of threshold? Let us see that now. So we use something called ROC for this, ROC curve. Okay, what is a ROC curve? So it is an acronym for receiver operator characteristics curve. Receiver operator characteristic curve. So don't worry about the name. You don't have to remember the name. Just remember ROC curve. Okay. So what is the ROC curve? It is a plot between sensitivity. So you have sensitivity on the y-axis. Okay. Which is the true positive rate. Okay. And you have the false positive rate. False positive rate or 1 minus specificity. Okay. On the x-axis. So it is a curve between sensitivity, which you already know, and specificity, which you already know, but it is 1 minus specificity, not specificity directly. Specificity is true negative rate. Okay. So 1 minus true negative rate is false positive rate. Okay. So it is a plot between these two. Okay. And it looks something like this. It typically looks like this. Okay. So what is this parameter? Tell me about the y-axis. Is this good or is this bad? Tell me, guys. Higher value of sensitivity, is this good or is this bad? Yes, this is good, right? This is how many actual ones are you predicting, or how many actual ones are you able to identify. So it is something good. And what is this? Is this good or is this bad? False positive rate. Yes, this is bad. So anything which starts with false is bad, and anything which starts with true is good. Always remember, okay? So this starts with false means false positive. False positive means you are saying it's a positive, but actually it is false. Okay? You are saying it's a positive, but actually it is a false. So this is bad. Okay? So what does this mean? This means that this is a good quantity and this is a bad quantity. So our goal on this curve, and what this curve represents different values of threshold. So your threshold starts from 1 here and it goes to 0 here. Okay? The threshold starts from 1 at the origin and goes till 0, opposite. Okay, always remember it is opposite. It doesn't start from 0, it starts from 1 and it goes till 0. Okay, now what would happen when your threshold is 1? So let's say this is probability of y is equal to 1, this is 0 and this is 1. What would happen when your threshold is 1? Tell me guys, what will happen? How many ones will you predict? If your threshold is 1, how many ones will you predict? If your threshold is 1, how many ones will you predict? Remember, what do? We say probability of y is greater than threshold, we say it's a 1, right? So if your threshold itself is 1, how many ones will you predict? 0, exactly. Shinu is right. We will predict 0 ones. Not all ones, Arpita. See, you look at this equation. Look at this equation. If your probability is greater than threshold, you are predicting a 1. And probability will never be greater than 1. So that means you will never predict a 1. So you will predict 0 ones. Okay. So if you predict 0 ones, what will be your sensitivity? If you predict 0 ones, what will be your sensitivity? It will be 0. Remember, sensitivity is true positive divided by something. True positive itself will be 0 because you are not predicting any positive. You are only predicting 0. So that is why you see this at origin. When threshold is 1, sensitivity is at origin. That means it is 0. Okay. So your true positive rate is 0 when threshold is 1. Okay. Now let us talk about false positive rate. What will be the false positive rate when your threshold is 1? So false positive is when you predict positive but actually it's a 0. That also will be 0. Right? That also will be 0 because you are not predicting any positive. So the true positive rate, the false positive rate will both be 0 because positive itself is 0. Positive itself is 0. So doesn't matter whether it is true positive or false positive, both will be 0. So that is why you have 0 for both x-axis and y-axis. So that means your error is 0, but your bad quantity, the quantity which you are trying to minimize is 0, but the good quantity is also 0. So it is useless basically. You are not making any error, but you are not doing any good also. Okay? You are not making any error, but you are not doing any good also. You haven't started yet. So that is what happens when you take a threshold of 1. So this is the extreme end I am talking about. Similarly, let us look at the other extreme. Now when you have your threshold at 0, how many ones will you predict? Going by the similar concept, if this is your threshold, how many ones will you predict? Yes guys, if your threshold is 0, how many ones will you predict? So this is your threshold. So whatever is above this is 1, and all the values will be above this, right? Again, same concept. Your threshold is 0, then all the probability will be above 0. So definitely you will predict all as 1. Look at this. Your values fall in this range, and you have kept your threshold here. So whatever is above this is all 1, and everything is above this. All probabilities will be above 0, right? So that means you are predicting all ones. Okay? Do you follow, Naresh? You will predict all ones when your threshold is 0. So that means even if somebody has 0% chance of having cancer, you are saying he or she has cancer. So obviously, if you are looking at 0% chance of having cancer, everybody will have above 0% chance of having cancer, right? So that means everybody has cancer, you are saying. Okay. So when you are saying all as 1, when you are predicting everything as 1, what will be the sensitivity? When you are predicting everything as 1, what will be the sensitivity? Remember yesterday's example, when we were predicting everything as 1, what was our sensitivity? So how many cancer patients will you catch? How many actual cancer patients will you catch if you are saying everybody has cancer? Tell me. Let's say if you have 95 zeros and 5 ones, 5 cancer patients you have, 95 do not have cancer, and you are saying all 100 have cancer. So how many actual cancer patients will you catch as a proportion? It will be 100%. You will catch all 5 of them. So this is what sensitivity measures, right? It measures what proportion of actual ones have you caught. And since you are saying everybody as 1, obviously you will catch these 5 also. So that means it will be 100%. If your threshold is 0, your sensitivity will be 100%. So that is why you see this. This is at the maximum, and this is 100%. Okay, this will be 100%. What will be your false positive rate in that case? Your false positive rate will also be high, right guys? Because you have predicted everybody as cancer, and 95 of them did not have cancer, but you said 1 for them. So your false positive rate will also be very high. So almost 100%. Look at this. So that means if you take a threshold of 0, you will end up with very high value of sensitivity, which is good for you. But at the same time, you will also end up with very high value of false positive rate, which is bad for you. Okay. So though you are getting a very good number at the good axis, but at the bad axis also you are getting a very bad number. So that means you cannot take threshold of 0 also. So that means there is a trade-off. There is a trade-off between this and between this. Here, your good quantity is 0, your bad quantity is 0. At this threshold of 0, your good quantity is 100%, but your bad quantity is also 100%. So that means somewhere in the middle we will have to take. Okay. So where should we take in the middle? We will select a point. We will select, so the threshold here is, it decreases. The threshold decreases slightly. So here it is, let's say 0.7. Here it will become 0.6. Here it will become 0.4. Here it will become 0.3 and so on. So what will we do? We will select a value somewhere so that we are high on the y axis and low on the x axis. Okay, again that will be a little subjective because different people might have different view, but that is how you take a call. So you will take, probably if I were deciding here, I would take probably this number. Okay, look at this number. I am almost 100% if I take a threshold of 60%. If I take a threshold of 0.6, I am almost close to 100% in sensitivity. And look at the error part. I'm very close to 0. Maybe this is 30%, but here it is 80%. So I get a sensitivity of 80% if I take a threshold of 0.6, and I get a false positive rate of 30% if I take a threshold of 0.6, right? If I take, let's say 0.7, if I take 0.7, then what am I getting? I'm getting 50% of sensitivity and 20% of false positive rate. So I could have selected this also, but the sensitivity also is very less in this case. In this case, I am getting very good sensitivity and somewhat less false positive rate. So maybe this is the best number. Do you follow, guys? Yes, you can just eyeball it. So looking at this, you can get the approximate value. Okay. Okay, guys, any doubts? So this is how actual ROC curve would look like. Okay, this is actual plot taken. I have pasted it here. Okay, so you see different values here. So this is the true positive rate or sensitivity, and this is your false positive rate. Okay, so here maybe somewhere around these three numbers, any of these you can take. You can take any of these thresholds, because you see you get almost above 80% sensitivity and the error is hardly 20%. So this is a good number. If you can take 0.1 also, but if you take 0.1, what would you get? You will get 90% sensitivity, but your error will also be high. Your error will be around 70%. So I will not take this. I will rather take this. Okay, because you get 80% accuracy and just 20% error. So this looks like a better number. You could have taken 0.8 as the threshold, then you will get 60% sensitivity and almost 0% error. Okay, so it depends on the business case. Let's say if you want to avoid errors at any cost, if you want to avoid false positive rate, then you will take 0.8. If you want to avoid false positive rate, you will take a threshold of 0.8. But if you want to increase true positive rate and yet have a less rate of false positive, you will take any of these. So it depends on the business scenario. What do you desire? And accordingly you take a threshold. Okay. Yes, guys, any doubts? Okay, now let us look at how do we get this in Python. Okay, let us see how do we get the same things in Python. So these are the codes for it. If you see, it is not very difficult. So after you get the predictions, now remember one thing, since here you will only get a ROC curve if you have the predictions as probability. Okay, because you haven't decided your threshold yet. If you have already decided your threshold, you don't need a ROC curve. Okay, so you get the ROC curve only if your prediction is a probability. It must be a probability. So don't apply a threshold and then run the commands for ROC curve. You will not get the ROC curve. You will get an error. Okay, only if your predicted value is a probability, you will get the ROC curve. If you have already decided your threshold, that means you have already decided your threshold. So the threshold should vary here. The threshold should vary. If you have already fixed your threshold at 0.5, it will not vary and you will get an error. Okay. So what do I have here? See, I have predicted the probability here by using the predict underscore prob a function, and this pred 1 is what I will pass to the ROC curve. So you see this pred 1 I am passing. Now this probability, if you see, it will be probability of, so this pred 1 will look like this. The pred 1 variable that you see there, it will look like this. It will give you the probability of both 0 and 1. Okay, but in the logistic response function, we have probability of y is equal to 1. So that means we will have to select this one. Okay, how will I select this one? I will use normal index operation. That is why I have selected the first column. First means the second one basically, because the index starts from 0. So this one means the second column, which is this. Okay, so this column I have selected, and that I am passing to the matrix.ROC curve function to get the ROC curve. Okay, do you follow this, guys? And these are just labels that I have given. Okay, I have shared one video also which will talk more in details about this if you want to know, or if you want to get a second opinion. This is the link I have shared. You can watch this video to understand this better. They will talk about this from a slightly different perspective. Okay, so the codes part is very easy. Just understand the concept, why do we need the ROC curve, and how do we understand or how do we interpret the different values in the ROC curve. That is what you should understand. This is very important from an interview perspective also. So this is type 1 error. Type 1 error is when you say it's a positive but actually it's false. Type 2 error is when you say it's a negative but actually it's false. Okay, so the doctor saying a man he is pregnant is a type 1 error, or it's a false positive. And the doctor saying a pregnant lady that she is not pregnant is a negative or type 2 error or a false negative. Okay, and there's one more thing which I missed. Let me come to that. So there is yet one more parameter that is used to measure the accuracy of any classification algorithm, and that is the area under curve. So let me talk about this. Excuse me. So that is the area under curve. So what is area under curve? So let me draw some ROC curves for you. So I'm drawing some ROC curves, okay? Let's say I have drawn this as one ROC curve. Let me draw this as another ROC curve. And there is one more ROC curve that I have drawn. Okay, let's say this, I have got this from model 1, I have got this from model 2, and I have got this from model 3. Which model is the best here? Which is the best model? Can you tell me? With this information, can you tell me if which of these models is the best, or you cannot say because I am not giving you enough information? Looking at this ROC curve, can you tell me which of these models is best? Of course, this is sensitivity, true positive rate, and this is false positive rate, or 1 minus specificity. Can you tell me, looking at this, which of the models is best? Or not enough information? Think guys, tell me. Do you think M3 is best? The reasons why? Oops, yeah. So the more the model is towards this side, top right, the better that model is. Okay. Or in other ways, what I can say is that another way to evaluate a model is by the area under the ROC curve. So area under curve, AUC. Okay. So you can clearly see that model M3 has the highest area under curve. The maximum value it can take is 100%. Obviously, you will never get 100%, but the closer to 1, the better that model is. So here, the area under curve of M3 is greater than M2 is greater than M1. So M3 is the best model, clearly. Okay, for the same reasons that you guys mentioned, but we can directly use the area under curve to evaluate that. So this area. Okay, so this is another parameter that is used. Let me see if I have calculated that in the codes. Yeah, so this is just one line of code you will use. Here I am getting 78%. This is the area under curve. Okay, just run this code and you will get it. Okay. Any doubts, guys? So this is what I have written here. I will share this explanation with you guys. Okay. So I'll share this entire explanation. So this is the same plot which I have shown you already. So this blue one is worthless. It is not at all good because you cannot find any point where you have less error and high accuracy. Pink one is okay, but yellow one is the best one. How do you convert Jupyter Notebook to PDF? It's very easy. Just go here, file, download as PDF. Okay. You can download it as HTML also, so that people who do not have Python can also read it. So you can download as HTML, as PDF. No, you don't have to install anything else. Of course, you should have PDF reader if you want to open. Okay. So guys, this is all I had for today.